Hello everyone. I'm Kuromeru. The goal of Series02 is to learn about left-invariant vector fields and left-invariant differential forms. Today, we're going to look into how the Jacobian changes when going back and forth between manifolds. Specifically, we want to see under what conditions the following calculation matches the Kronecker delta. Let's get started. First, I'd like to talk about why we consider this question. For CR-class manifolds M and N, we transform the tangent vector at a point P of the manifold by using the differential map DFP of a CR-class map F. We consider a linear map DG TFPN to TPM, which serves as a kind of left inverse of DFP. Though DFP is not invertible in the strict sense due to the difference in dimension. After carrying a tangent vector from the world of M to the world of N, we then bring it back to M. The question is, does this tangent vector return to its original state? From now on, let JFP be the matrix representation of the differential map DFP. We assume that the Jacobian JFP has the maximum rank possible for its matrix size. We have taken x as the coordinates on an open set U of M and y as the coordinates on an open set V of N. Also, let JG be the map that sends the tangent vector at FP back to the coordinates at P. Let x in TPM be a tangent vector written in components as follows. The entries of the matrix JGJF is as follows. If this equation holds, then JGFPJFP is the identity matrix. So this equation means the vector returns to its original state. If this equation doesn't hold, then this equation means the vector does not return to its original state. To give the conclusion first, if going to N reduces the degrees of freedom, in other words if dim M is greater than dim N, then the vector will not return to its original form and the above equality will not hold. Conversely, if dim M is less than or equal to dim N, so that the information of the vector can be fully preserved in the back and forth process, then the vector does return to its original state and the equality holds. From here on, I will give a proof of this. When the dimensions of M and N are equal, this forms the basis of our discussion. This is known as the inverse function theorem, and we will accept it without proof. What this theorem states is, if the Jacobian JFP is a regular matrix, then there exists an open neighborhood U of P and an open neighborhood V of FP, such that F is a CR-class local diffeomorphism from U to V. From this, JF inverse exists, and JF inverse composed with JF from TPM to TPM becomes the identity matrix. Therefore, in this case, the following equation holds. Here, we assume that JFP is a regular matrix, and that the dimension of M is greater than the dimension of N. To make the idea more concrete, let's look at an example. Let M equal R3 and N equal R2. And consider subsets where the coordinates are positive. Define a map G from N to M, where Y maps to X as follows. With this definition, the inverse map F is not uniquely determined. For example, we can define it as follows. Alternatively, we can define it as follows. We apply JFI and then JG in sequence to the basis vector partial x. This gives the following result. We will show that this is not an equality. In either case, the transformation JGJF at a point P in M, that is, the Jacobian of the round trip from the tangent space TPM, has rank 2 in both cases. This means the resulting Jacobian matrix of the composition cannot be the identity matrix. And thus we can see that JG composed with JF is not the identity matrix. Let's actually do this for F1. We can calculate it as follows. So we can clearly see that it is not the identity matrix. And for F2, we get the following result. And here again, we can clearly see that it is not the identity matrix. This can be interpreted as the loss of degrees of freedom when mapping from M to N, which causes the identity map to break down. Now let's try the reverse. We send an open neighborhood in the original space to a higher dimensional space, and then try to bring it back. This time, we swap the roles of x and y from the previous example. Let's define a map Fm to N as follows. Then, the inverse maps can be given as. In both cases, the composition GIF equals ID M holds. Now, if we compute the Jacobian products JGJF, we find that both give the 2 by 2 identity matrix. Let's compute this for G1. We get the following result. And for G2, we get the following result. Let's prove this result. That is, we'll show that this is an identity. We add one more variable, z, to the domain, M, so that the Jacobian, JF, becomes a regular matrix. This allows us to apply the inverse function theorem. Let's denote the new coordinates by y hat defined as. Under the assumption that the inverse function theorem applies, we can locally invert this to get. In this setup, the product of the Jacobians JG prime, JF prime becomes the 3 by 3 identity matrix. Just like in the case where dim M equals dim N. From this full identity matrix, we can extract a smaller identity matrix by trimming rows and columns. That's the core idea. Note that although the entries of the inverse Jacobian JG may change depending on how Z appears in Y at this point, removing the corresponding row and column still yields the identity matrix. Please pay attention to whether Y has a hat or not. Now, what we need to do is to show the matrix equality. This implies that the following equalities hold for each component near Z equals 0. To do this, we use the differentiability of coordinates. Since we are working with CR manifolds, we are allowed to use this property. The differentiability of a function f of m variables means that for any direction h approaching the origin, there exists some f prime a in Rm, such that here the dot represents the dot product of n-dimensional vectors. Let's begin by showing this. On the left-hand side, we take the partial derivative, while z still has its degrees of freedom, and then set z to 0. On the other hand, on the right-hand side, we first set z to 0, and then take the partial derivative. Now, because condition formula 1 holds, we can exchange the order of limits, meaning it doesn't matter how we approach the evaluation point. Thus, we've obtained the desired result. The same argument applies to other partial derivatives, partial y, partial x, as well. Now let's compute partial x, partial y. It looks like this. This proves the result. Other components of partial x, partial y, follow similarly. Therefore, by trimming JG prime JF prime, we obtain a smaller identity matrix, which turns out to be exactly JG-JF. The extension to higher dimensions is straightforward. We can proceed in the same way by exchanging the limits. The key point is whether the inverse function theorem can be applied or not. Now, let's consider the case of Lie groups. In this setting, we always have dim m equals dim n. Let's confirm with an example that JF inverse JF gives the identity map. We take the two-dimensional Borel subgroup G. Let H and G be elements of G, defined as follows. Here, both A and X are non-zero. The tangent vectors at G in TGG are as follows. In general, the action of a Lie group can be thought of as a movement within the space. Here, we want to consider the left action of H on G, interpreted as a differential map. This is what you get when you move G by H. We denote this by the left action LH. When it acts on tangent vectors, we write it as the differential map DLH. For example, the form of a certain DLH xg is as follows. So under this action, x maps to ax, y maps to ay plus b over x. Therefore, the push forward of the tangent vectors becomes Now, let's consider the inverse action. So we have the following. Here, x and y are expressed in the coordinate system at the point hg. Now compute the differential of the inverse action. Partial x is mapped to partial x. Partial y is mapped to partial y. Perfect. We've shown that DLH inverse DLH equals ID TGG. Similarly, we can check that DLH inverse equals ID THGG by substituting the coordinates of H inverse into those of H. In this video, we explored the behavior of the Jacobian under round-trip transformations between manifolds. I hope this helps deepen your understanding. That's all for today. If you enjoyed this video, please subscribe to the channel and give it a like. Your support motivates me to keep creating more content. Thank you for watching.